Hello, everyone. This is Professor Jeff Wilkerson at Luther College, and what we're going to talk about here today is a little bit of the difference between accuracy and precision, how that relates somewhat to how we're trying to measure uncertainty in our physical measurements in the physics laboratory. This is primarily an introduction for the Physics 152 students for their first lab. It's going to happen on February 3rd this week. And so that's primarily what we're doing, although the ideas are a little bit broader than that and might be of interest to other people out there, and we might use them in other courses here as well. So we'll start with this idea of accuracy and precision that you may have seen elsewhere. And the precision is really referencing, when we talk about it in the physics lab, it's referencing the spread of the measurements to say that the measurements can be spread across some area, and that spread is telling us what the precision of those measurements is. You make any one measurement, and it could fall fairly likely. It might be denser here in the middle and then fan out and spread out toward the edges. But it could fall, you have a fairly high likelihood of probability of it falling somewhere in this range. And what could give rise to that precision could be all kinds of effects. It could be a sort of a background noise. It could be a scatter in your ability to read an instrument. It could be just a scatter in the thing that's actually being measured. It could be all sorts of ideas like that say, you measure one time and it's here, you measure another time and it's here, you measure another time and it's here, you measure another time and it's here. That's what these dots are. They're individual measurements of a quantity that we assume isn't changing between measurements. So you have these individual measurements and how precisely you can measure those. Now you can still centroid that distribution pretty well. If you take a lot of measurements and average them all, you can figure out where the middle is. Do a pretty good job of that, okay? And so you can find this centroid, the center of this distribution, pretty well. Now, whether that center of the distribution that you measure is actually mapping onto the center of the distribution of the actual quantity is a different question. And that's where accuracy comes in. So this spread across here is precision. Whether or not that center, that mean that you measured, so you measured the average of the distribution, how close that mean is to the actual mean, the actual value of the thing that you're trying to measure, is a question of accuracy. So let me give you an example here. When I take data up on the rooftop, click, 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 but that's a different thing. What we're doing there is we're measuring the brightnesses, how bright a star appears to us, of about 1,640 stars every single night. And we do that by measuring a whole bunch, taking a whole bunch of images, bam, 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 and averaging the signal in all of those images. Okay? Now, from one image to the next, what we measure for the brightness, the signal from that star can vary quite a bit. Okay? And it depends. If it's very faint, the things that lead into that star varying in brightness include counting statistics, Poisson counting statistics in our conversion of light to photoelectrons in our detector, and then Poisson counting statistics in the digitization of that signal, of those electrons, and noise, and then counting statistics in the noise of the on the line of that signal, and then light being scattered out by the atmosphere, what we call scintillation in the atmosphere, so scattering of light has a counting statistic. So all of those things cause us to not measure the same thing every single time. And that's precision. We're gonna have a distribution of signal measurements across here, and that's sort of the precision that we're talking about. And we will measure that distribution here as a standard deviation, which will often give us a symbol sigma like that. And so that's our standard deviation that we're talking about. It's a measure of that spread. It's a measure of that precision. Now, whether that's an accurate measurement of how bright the star was on that night is a different question. The mean value, which we'll often give the Greek letter mu to, the mean is our best estimate of how bright the star was that night. And so that's our best estimate of the star's brightness. But whether that actually matches what the star is fraught with all kinds of problems. Our ability to measure blue stars, so the light being scattered by the atmosphere, for example, is different for blue stars than it is for red stars. And so our normalization, the way we try to calibrate our data, might be different for blue stars and red stars. And we have a calibration curve that we apply that is a function of the color of those stars. And it's not going to be perfect. And we might be missing on one end or the other end. And we might miss low or high always. And even it may not even be color dependent. It may depend on nights that have a lot of moisture in the atmosphere versus nights that have less moisture in the atmosphere. Might cause us to miss high or low when we're comparing to some standard that was taken on some night of unknown moisture in the atmosphere, for example. And so this is often can slide around just a little bit. The way you'll see this a fair amount out there is to say, if you're shooting arrows at a dartboard, you want to try to shoot a tight group. And so you want to try to shoot all of your arrows in a very narrow space. And that narrow space is a measure of precision. That means you're shooting very precisely. But if that tight, precise group isn't on the bullseye, then it's somewhat inaccurate. You're measuring an inaccuracy across there, the distance from the bullseye. So you've got two different quantities. How much spread is there, and how much is that group distant from where you were trying to get that group? And so those are ideas, the concepts that we're going to practice in the lab this week, and we're going to practice throughout the semester. We're just getting started to warm us up because we're going to do great stuff. We're going to measure a lot of fun stuff in the lab this week, this semester, and this is getting us going in this direction. So what we're going to do, we're going to actually, for the Physics 152 students this week, if that's who you are watching this, hopefully this is interesting for you even if it's not, but for the Physics 152 students out there watching this, in the lab this week, we're going to take some electronic devices called resistors, which we'll work with later in the semester, but we don't care about what they are exactly right now. We're just going to look at those resistors and identify these concepts of precision and accuracy, and to say, if you get a whole bunch of resistors that all claim to have the same resistance value, how much spread is there from one to the other, and how much can the mean value of that distribution of resistances, how much can that mean value vary relative to what the claim by the manufacturer is the resistance value is. And so we're going to play with that idea just a little bit. I think I'm going to have fun. I think you'll have fun too. And so that's what we're looking forward to this week. And it's going to help us think about how we process data and think about how we answer questions about the universe all throughout the semester. And that's our goal for the semester. We have a few learning goals, but our primary learning goal is to just get better, more nuanced at the way we approach making meaning out of measurements in the laboratory. And we can take that and apply that to any setting you find yourself in. You find yourself in this lab or doing this thing or doing this thing. This is an idea that we can apply. So what we're going to do is we measure a whole bunch of times. Again, we think we're measuring the exact same thing every time. And if we're measuring the exact same thing every time and we make multiple measurements of it, we can make a histogram. We'll work on that later. We're going to do that next few weeks. But we can make a histogram of the values, and we can fit a Gaussian curve to that histogram. But again, that's in a few weeks. Right now, all we're going to do is we're going to take the mean and the standard deviation and say our best guess is equal to the mean, and our uncertainty is equal to the standard deviation divided by the square root of number of trials, or so the standard error, we would call that. So if we measure 25 resistors, we take the spread of that standard deviation of the measurements of those 25 measurements and divide by the square root of 5, that's going to give us our uncertainty in the mean. We're going to go mean plus or minus sigma over the square root of n. Now, that is a one standard deviation uncertainty. If these things are distributed according to a Gaussian distribution, which we assume that they are, we'll talk more about that as the semester unfolds, then we would say, they might not be, but we would say that there is about a 2/3 chance that just by random chance, just by the noise, just by the lack of precision in the measurements that you have right here, that there's a 2/3 chance that your actual mean falls within plus or minus one standard error, like that, one standard deviation. If you do 2 standard deviations, that's your 95% confidence level. Some of you may have heard about a 0.05 type measurements. We'll talk about that as we go on too. So we could say if it's two of these error bars, you got a 95%. You got a 5% chance of the mean actually falling outside of the range of those two. And so we're going to work on that just a little bit. Looking forward to getting started on the lab. Hope this idea of precision and accuracy is interesting for anyone who's out there watching it. And we'll have more as the semester goes on. Thank you, everybody. Have a good week.